Good morning, good afternoon, good evening, or good night. Wherever you live, I hope you're all doing well. And welcome to my presentation. My presentation is about Plusmine, which is our dynamic active learning approach with semi-supervised learning for automatic classification. My name is Jan, and this research is done together with Sandjai Bhulai, Mark Hoogendoorn, and Rob van der Meij. And we are from the CWI, Centrum Wiskunde Informatica, or Center for Mathematics and Computer Science, and the VU University, or the Vrije Universiteit Amsterdam. So let's start with the research motivation. So our research is in cybersecurity, and there, of course, are some problems in cybersecurity, there are problems in any field. So in cybersecurity, we have enormous data sets consisting of millions of connections between computers or hosts, and only a small fraction of these observations are interesting and possibly malicious. This is not in itself a problem, but the problem is that there's a lack of labeled data because it's very time consuming and tedious for a cyber expert to label data. So that means it's difficult to deploy, assess, and compare performances of network intrusion detection systems. So yeah, we have a need for a network intrusion detection system that is able to learn from small sets of labeled data because we have few labels available, that are able to make predictions on large sets of unlabeled data because of these enormous data sets. And also we want to look for a way to select the most interesting observations for labeling, such that we can label as efficient as possible. So that means we want to combine human expert knowledge with machine learning. So I think the next figure illustrates that very well. So this field of machine learning is called active learning, or AL. And what we see in this illustration from Deep AI is how this whole framework or this whole paradigm works. So we start with a small labeled data set, which you can see on the left. So you can just see a look at, in this setting, a cyber data set. So we just have these connections as observations. They all have like feature values, like duration of the connection and so on. And we have a label. And in our setting, the label is binary. So we have a benign connection, so harmless, or we have a malicious connection or harmful connection. And what we do then is that we train a supervised classifier, an intrusion detector on this labeled data set. And when that is done, then we apply it to the unlabeled data set. So this huge pool of unlabeled data. And we make predictions about the connections that are in that unlabeled data set. And we can also use some other machine learning methods to derive some statistics from this unlabeled data set, like clusters, for example, anomaly scores, things like that. So we can collect multiple information metrics of this data. What we then do in active learning is that we have a query function, and this query function determines, or this one selects, the most interesting or the most informative observations from the unlabeled data set. And those observations are presented to the human expert. So the human expert in this illustration is the brain with glasses, which is, I think, a very nice representation of a human. And then the human provides the real label of the observation. And then those observations with the real labels are added to the labeled set. And then we continue this process until some stop criterion is met. For example, when the human expert is tired, things like that. Yeah, an important thing is whether an observation is interesting or informative. And usually what happens in active learning is that we look at how much does the observation contribute to improving the classification performance. So that's what we do. So we proposed an active learning method called Yasmin, about which we made a paper, and we submitted it to the journal Machine Learning with Applications, and it's accepted as a minor revision. But yeah, to give a summary about Yasmin, so we have a hybrid method. So that means we want to improve this performance by querying 3 observation types, which are uncertain observations, anomalous observations, and random observations. So we look at different types. So for example, to give an illustration about that, uncertain observations, those are observations about which the intrusion detector is not really sure about. So let's say we have the binary case. We just get the model gives a malicious probability. So a probability of 1 is that the model is really sure that the observation is malicious or a cyber attack, for example. And 0 means that the model is very sure that the connection is benign, so harmless. And of course, if the model is not sure, then it will give some kind of probability close to 0.5, for example. That's intuitively in between 0 and 1. So maybe those observations are really interesting, because if those observations really get the real label, then the model can really learn from that, because beforehand the model was like, oh, I don't know what, if it's benign, if it's malicious, I don't know. But then the model gets the real label, and then it knows like, oh, okay, so it was malicious or it was benign. So then it can learn better, hopefully. And the important thing of Jasmine is that we have alpha dynamic updating, it's called. And that means that we are able to balance how many uncertain observations we want to query, how many anomalous observations we want to query. We can update that through the labeling procedure, because it can happen that for a specific data set, for example, it is better to almost exclusively query uncertain observations. For another data set, it's maybe better to show a lot of anomalies, for example. So we want to learn during the process which observations are better to show to the human expert. So yeah, that means with Jasmine we had good performance, and it was also robust. So it means that it was able to adjust itself to the structure of the data. But there are still some limitations, and that's actually a limitation in the whole field of active learning, because we are still limited by the labeling speed of the human expert. To give an illustration, so what we do, we train a classification model, so an intrusion detector on the data. Then we have this query function and stuff to select the unlabeled observations, which are the most informative. And then we show them to the human expert, and then the human expert starts labeling. But while the human expert is labeling, we are just waiting for them to finish labeling, and we cannot do anything else, because yeah, the model is already trained and stuff. That takes less time than the labeling part. So that's finished earlier than the labeling. Yeah, so we want to look at how can we make correct predictions even faster than this active learning approach. And that's why we want to incorporate semi-supervised learning. And that's important to know. That's the contribution we make in this paper. So we have the previous illustration we had before, but now we made an adjustment to that, or we added another component. And in the design of the illustration, you can really see what we added. But I think that's also good, because now it really stands out what was added to the picture. So we have the same thing, but now for the unlabeled part, for the unlabeled pool, you can see that we also choose observations to automatically label. So we still have the active learning part. We still select observations to be labeled by a human expert, but we also want to select observations that we are going to automatically label, so that the observation that the model is going to label those observations by itself with the predictions. Yeah, so how do we do that? So we have this question, or we actually have two questions, when and how to label automatically. So yeah, as we said, the query function is there to determine which observations are shown to the human expert to get the real labels. But we also want to automatically label observations with their predicted class when some condition holds. And to give an example of such a condition is the research by Tomanek. They propose certainty labeling, which means when the confidence of a model in its prediction exceeds some threshold tau, then the observation is automatically labeled, which intuitively makes sense. So let's say the model is very sure about the label, then maybe you want to automatically label that observation, because then, yeah, the model is really sure. So why would you even show it to the human expert if you already know, or you're already quite sure what the label will be? But there are some problems with this, because this tau is highly dependent on the data and the classifier you use. So let's say if you take tau too small or too low, that means that the confidence can be, a lot of observations have a confidence above this threshold, which means that at the start, an enormous number of observations are already automatically labeled, usually with the wrong label because it was trained on a really small data set. So that means it cannot generalize well. So it means you make a lot of wrong predictions, and it's really difficult for the model to recover from that in the next steps. But if you choose tau too high, that means that you are never going to label anything automatically, because then the confidence never exceeds that threshold, and then you just revert back to active learning. So important to note is that we already have active learning, but we're going to add this automatic labeling part to it. And another question here is labeling based on confidence even the best strategy? So that's why we are going to introduce a new strategy for automatic labeling, which we will call Plusmine. So Plusmine is our active learning method with automatic labeling, and we do that with semi-supervised learning. So Plusmine consists of two components. So it consists of the active learning component, which is based on Yasmin. So it's not completely Yasmin. We made some adjustments to it, and we will show later that they are actually improvements. And we also have the brand new component, which is automatic labeling. And we determined it as follows. So we have a small algorithm, and hopefully it will become clear. So we start with to construct all the feasible observations for automatic labeling, and we call that set A. And actually, A is just the complete set of unlabeled observations minus the query set, because the query set is already what we are going to show to the human expert. So that means that we don't have to make them a candidate for automatic labeling, because getting the real label by the human expert always trumps giving an automatic label or a predicted label. So we have this set A of candidate observations. What we then do, we randomly take, without replacement, S subsets of size B from A with predicted labels to obtain S subsets, so candidate subsets. So let's say we take 30 subsets of size B from A, so then we get 30 candidate subsets of size 50 each. What we then do for each candidate set, we add it to the labeled set that we already had, and then we train that. We train the classifier on it, we train a classifier on it, and we validate it, just a usual train test split, and then we get some performance we call phi. And then what we then do, we choose the candidate set that gives the biggest phi, so the biggest performance. So what we actually do, we have these 30 candidate sets, and we select the candidate set that we expect to increase performance the most. So actually we have the same goal again as with active learning, because with active learning we wanted to select the observations that are expected to increase performance the most, but we're actually also doing that in this case. We also are going to select the observations that we expect to increase performance the most. But with active learning we have the human expert giving the real labels, but now we have the model giving predicted labels. Yeah, so of course, to see if this works, we did some experiments. So we used the NSL KDD dataset and the UNSW ND15 dataset. So these datasets are, so the NSL KDD is very well known in cybersecurity, but they are both datasets, cyber data with simulated networks of hosts with benign traffic and cyber attacks in them. And then we executed the procedures we talked about before. So Plusmine, so our method. Then we also executed Plusmine incomplete. And actually Plusmine incomplete is just the active learning component, or it's just Yasmin, but with the adjustments we made to it, so the improvements. So we just want to see, we use this to see if the adjustments we made are actually good. We have this Tomanex certainty labeling, which we just talked about, this confidence level tau procedure, and we have the Yasmin procedure as a kind of baseline performance. And of course, during the experiments, we chose different hyperparameters like the initial set size, so how big the labeled set is at the start, so L0. We have Q, which is the size of the query set, how many observations we're going to show to the human expert, each iteration, and so on and so on. So we have these results. So these are some results, and maybe they are a bit overwhelming now with all the curves and all the colors and all the graphs. Important to note is what you see here. So in each plot, on each figure, you see an x-axis, which is the size of the labeled set with real labels. Because of course, when we have automatic labeling, the labeled set increases much more quickly than if we only have active learning. So that's why we only look at the real labels, because then we can compare the sizes, the number of real labels we have in the labeled set. And on the y-axis, we have the performance, in this case, the F1 score. And what you see here, the curves are the learning curves. So you can see how the performance increases or decreases when more observations are added to the labeled set by means of active learning or by means of automatic classification, stuff like that. Plusmine, so our method, is the dark blue curve. And what you see in these figures is that it's usually the best, or it's when it's not the best, then it's really on par with the other model, which is really the best. And here we have like different data sets, different dataset configurations. We have different intrusion detectors. So we have decision tree, gradient boosting machine. So we did a lot of experiments. Yeah, so there are some, this was maybe a bit overwhelming, but there are some crucial observations, I would say, or remarks. We see that Plusmine performs better than or on par with the other procedures, which means that adding automatic labeling is beneficial to the performance or is beneficial to the procedure. We also see that Plusmine is more robust on average, and we have less erratic behavior. We can see that in two ways. We can see that here in the graphs, you can see that the dark blue curves are jumping much less than the other procedures, but also these are average curves. So we did multiple runs. And also if you look at the variance in these learning curves, in these runs, and we can also see that Plusmine is jumping less. So it has a smaller variance. And what we also see is that Plusmine quickly reaches its final score or even surpasses that score, which is also really interesting. So the black dotted line is the final score. So that means the score you would get if all the data was labeled, then you would get that performance. If you train a detector on that, an intrusion detector, and you can see that for some configurations, you can see that Plusmine already performs better than that final score. So that means that with less data, it can get a better performance, which is also really interesting. We also see that Plusmine incomplete, so that's the active learning component of Yasmin with the adjustments we made to it, and Yasmin itself as the baseline, they usually perform similarly, but Plusmine incomplete has less severe performance drops. So you can really see that in the top right picture. You can see that on average, Yasmin like crashes down, and it has has a lot of difficulty to recover from that. And Plusmine incomplete, which is just active learning with some improvements to it, it behaves already quite steadily or quite robust, and it doesn't have this performance drop. So it's really nice. Yeah, we also see that the GBM intrusion detector, so gradient boosting machine intrusion detector, performs better than a decision tree, which is not really surprising because the decision tree is just one tree, a very simple, weak predictor. And a gradient boosting machine is a boosted tree-based algorithms with a lot of trees in it. Yeah, so you also expect that to perform much better. But it is surprising that the decision tree still performs quite well. So if you look at the top two figures, the score is already quite high for just one training, just one tree. So that was maybe the surprising part. Yeah, but of course, more results and an extensive analysis, they are all in the paper. So I would suggest you to read the paper. So some conclusions, so the contribution. So we introduced Plusmine, which is our active learning approach with semi-supervised learning as automatic labeling. It is an extension and improvement to the active learning method Yasmin that we also talked about in the start of this research. We performed automatic labeling. So the contribution we have by selecting a subset of observations that are expected to contribute the most. And we also see that that indeed happened, indeed was the case. And we showed that Plusmine performs better than the benchmark methods. So yeah, that was it. So I want to thank you for listening. And if you have any questions, just let me know. And you can also always send me an email on this email address. So I want to thank you for your attention.